Hi, do you know about the calculus? Do you know what is the differential of a function, or of a variable dy, dx? Do you know how they are defined? There was a time when mathematicians agreed that dy equal f prime of x times delta x, where delta x was denoted as the increment of the independent variable x and f prime of x as its derivation. But what is dx? Mathematicians assigned dx as equal to delta x. There were many kinds of methods to define it as delta x. Some textbooks stated that it was because dy equal dx, when y equal x, while some said it was because dx equal delta x for the function x equal x. But it's ridiculous to use a special notation in general cases. Nowadays textbooks gradually incline to define differential dy of the function y equal f of x as a map, turning any real number h to f prime of x times h. Especially, dx is denoted as the differential of the identity mapping. And therefore dy equal f prime of x times dx means the relationship between two functions' differentials. This was originally proposed to avoid the mistakes mentioned above, but it is obvious that special notations are abused in general cases. And it still fails to reflect the essence of differentials. How confusing! What is dx on Earth? In fact, you are not the only one puzzled by the problem of dx. This problem, or to be more fundamental, the essence of infinitesimals, has confused generations of mathematicians. The differential notation dx, as well as the integral notation, which are familiar to us today, are adapted from Leibniz, who invented the calculus method in 1673. In his system, differential is described as the difference between two variables, which are close to each other as closeness can be, while integral is defined as the point-to-point accumulation of differentials. As Leibniz said, it will be sufficient simply to make use of them as a tool that has advantages for the purpose of the calculation. He looked on his calculus as a tried method more than anything, but it was difficult to demonstrate the essence of calculus. His infinitely small was as small as you please, or in other words indefinitely small. This can be viewed as the original edition of today's question, what is dx? Almost at the same time, Newton independently created the calculus method system in 1665 to 1668. Here we ignore the dispute of priority between these two pioneers, but only sketch out the content of their theories. Newton artificially introduced a small number, O, to establish a fluxion, basically equivalent to the derivative we talk about today. However, his O was equal to 0 when used as the remainder term, but not equal to 0 when used as the denominator. There existed a logical contradiction in Newton's system. For this reason, George Berkeley, the British Bishop of Cloyne in the Northern Ireland region, ridiculed that Newton's O was a ghost. Since then, the question about the essence of infinitesimals and the underlying logic of the calculus has continued to trouble people generation after generation. In 1821 to 1823, Cauchy fabricated the mathematical concept of limit and interpreted the so-called infinitesimal as a variable whose limit was 0. He and his successors grafted Leibniz symbols into Newton's system, making the principles of calculus almost what they are today. With the prevalence of formalism, new questions emerged. Mathematicians employed logically rigorous tools in concocting a host of strange counterexamples. Driven by these questions, Cantor, Lebesgue etc. established the theory of real numbers and integral theory, and it was declared that the calculus system had been complete. Later, Robinson tried to return to Leibniz thinking and created non-standard analysis, which sparked a new wave of research. However, these theories are far from mature to reveal the essence of infinitesimals and provide new methods for practice. Until now, there are still many people who are skeptical of Cauchy's calculus principle, and attempt to explore the essence of infinitesimals. Chinese mathematician and philosopher Ding Xiaoping systematically solved the problem of the calculus principle about 10 years ago. How did he make it? In next few sections we will elaborate on his criticism of the current system, present his interpretation of differential, and briefly introduce how he reconstructed the calculus principle system by establishing a new number point model. For the entire discipline of calculus, the occurrence of methods preceded principles, which is common sense for anyone who knows a little bit about the history of calculus. The principle of calculus is the logical system to answer why calculus method is effective. What is the correct way to reveal the calculus method, and how to reveal more calculus methods? The number point model in current mathematics cannot describe principles of calculus, leading to the failure of establishing a complete, rigorous and scientific system of principles of calculus. The fundamental difficulty in establishing principles of calculus, based on the current number figure model, is to deal with the OX delta x in delta y over delta x equals f of x plus OX delta x. If we leave out the OX delta x, f of x can be written as the form of the differential quotient. However, the bridge between the integral and the differential, or the derivative, does not exist. If we keep OX delta x, f of x cannot be written as the form of the differential quotient, and the integral in the Leibniz form is out of the question. By means of the limit, we can remove OX delta x. However, f of x still cannot be written as the form of a differential quotient. So mathematicians, headed by Cauchy, roughly set up principles of calculus in non-scientific ways, which was the source of all ridiculous things in the area of principles of calculus. In last section, we had know the definitions of differential, then we will introduce the criticism of the current principles system of the calculus. Let's begin with the mistakes of current principles of differentials and derivatives. As a general rule, for y equals fx, x is the reason, while y is the consequence. In the meantime, y is the reason of its consequence, x is the consequence of its reason. This kind of relation has neither beginning nor ending, which is the law of the world. Its reflection on mathematics is z equals ey, y equals fx, x equals gt. Therefore, unless x equals t, we should admit delta x is not equal to dx because of the formula 1. Someone may say that x is the original variable, thus x equals t always stands up, so dx equals delta x. We may ask, if this argument made sense, what we could say about the derivatives of the implicit functions, what we could say about the derivatives of the parametric equations, and what we could say about the second substitute method for indefinite integrals. What we discussed above is the situation of one variable. It's more ridiculous when we turn to the calculus of functions of multivariables. Set a function of m variables fx equals fx1 until fxm, which is defined on a neighborhood of the point x0 equals x01 until x0m. If there exists a I in R, I goes from 1 to m, for delta x equals delta x1 until delta xm sufficiently small. We have formula 2, then we can say that function f is differentiable at the point x0, and we name this as the total differential at x0, which can be marked by formula 3, when we make the convention formula 4. In fact, if we replace each variable xi with a differentiable function xi equals xit, where t from t1 to tk, I goes from 1 to m, therefore, according to the chain rule for computing the derivative of composite functions, we have formula 5. Thus, it is ridiculous to define delta xi equals dxi forcibly, or make the convention of the same thing. If we expect to make a deduction in Cauchy's style, we have to stipulate x equals xi, where I goes from 1 to m. Thus x1, x2 until xm all equal x can be deduced. However, in this way, functions of multivariables will degenerate into functions of one variable, which is absurd. In a word, the premise of current principles of calculus is that the increment of the independent variable of a derivative itself is always equal to the linear part of this increment, regardless of whether the increment grows according to linear or nonlinear relationship. Is this premise reliable? As stressed in previous video, the so-called system of principles is a law group that reflects the intrinsic link of things. The system of principles of the calculus is an interlocking law system that explains the intrinsic link of calculus methods. In Ding's opinion, the current principles of calculus established by mathematicians headed by Cauchy fails to reveal the intrinsic link of the calculus methods. Today we will introduce his critique on integral and solving differential equations. Let us make a comparison between Cauchy's and Leibniz's systems. According to current system, indefinite integrals and definite integrals are not unified integrals. The definite integrals is the limit of the sum, whereas sometimes the indefinite integral is the inverse process of taking the derivative, and sometimes the indefinite integral is the inverse process of the differential. Only when calculating, the definite integrals refers to the indefinite integral. Are these operations reasonable? In Leibniz's system of principles of calculus, d represents the differential, dx represents the difference between two adjacent points, and the integral operational represents the operation of summation. That is to say, the differential is the miniaturization of a certain interval at the point level, and the integral is the accumulation of the result of miniaturization at the point level. The differential is the inverse operation of the integral, and vice versa. There exist no essentially two different kinds of essentially different integrals, or to say, definite integrals, and indefinite integrals are unified in theory. And the derivative is the differential quotient. By a comparison of the two, it's not difficult to see that Leibniz's system are the real fundamental calculus principles, while the current system of principles of calculus, represented by Cauchy's theory, fails to hold water. Firstly, the current system of calculus principles fails to reveal the inherent link among the differential, the derivative and the integral. Moreover, it breaks up the link between indefinite integral and the definite integral, which should have been two aspects of the same thing. If there is a link between them, it's just that the latter draws support from the former in calculation. Secondly, in the current system of calculus principles, the derivative is acknowledged as the instantaneous rate of change, and that the derivative is the differential quotient, but the differential is not an instantaneous volume. Consequently, there exists no instantaneous change rate. Therefore, the integral fails to be the inverse process of the differential. In this way, the differential is a monster from nowhere, and its application is no more than the approximate calculation, whose accuracy is much lower than series methods. Thirdly, the separation of variables is a classical method to deal with differential equations, which is to transform all derivatives into differential, and taking integrals at both ends. This effective method reveals that the integral is the inverse process of the differential. Here we take integrals at both ends for differentials instead of anything else, which are integrals in Leibniz's sense. Clearly, the current system of calculus principles, which interpret integral as merely the inverse process of derivation, cannot reveal any inherent link in the differential equation completely. After separation of variables, the ordinary differential equation is converted into this form. Then we take integrals at both ends, Thus we get the general solution hy equals gx plus c. However, problems raise up after a serious check. The original ODE implicitly determines a function y equals fx, and we can write it as the form as this. It reflects the methodology to solve the equation. If we admit dx equals delta x, thus the integral of dz equals g prime x dx can result in gx plus c, but the integral of h prime y dy cannot result in hy, because according to the definition of the differential, dy is the linear main body, which is fx delta x equals fx dx. Whereas we know dy equals fx delta x, but doesn't equal delta y, thus we get dz over delta y equals h prime y, doesn't equal dz over dy. Therefore, the integral of h prime y dy cannot result in hy. Someone may say that the indefinite integral is also the inverse process of the differential, so that the inverse processes of taking the derivative and taking the differential are the same indefinite integral, namely fx plus c. This is wrong. Though the result of the inverse process of taking the derivative and that of taking the differential are the same fx plus c, the specific integral of fx dx itself can only be the inverse process of one of these two operations. Because taking the derivative and taking the differential are not the same thing. If it was the inverse process of taking the differential, there should exist integral of fx dx equals the integral of dfx equals integral dy. Thus when we used the second substitute method for integrals, according to the fundamental definition of the differential, namely dy equals fx delta x, we had integral of dy equals integral of fx delta x, where delta x equals the sum of phi prime t delta t, and ot delta t multiplied by delta t. In this way, we could find that its linear main body, i.e. the differential, was dx equals phi prime t delta t. Therefore, we have the equation as this. Could be deduced, which is obviously wrong. Why can the theoretically chaotic principles result in right conclusions? This is because the form of dz equals h prime y dy is right in sense of Leibniz's system, where the dy, dz, and the corresponding principles. The definition of the differential are different from those in the current calculus system. In the current system of principles of integrals represented by Cauchy's theory, the indefinite integral is the inverse process of taking the derivative. But when facing equations of derivatives, this kind of indefinite integrals is helpless. And we have to transform all derivatives into differentials, and take integrals at both ends in Leibniz's way. Isn't it absurd? As we all know, a complete set of principles of calculus should include both the one-variable situation and the multivariable situation. And it also should step from one order to the high order. If the current system of calculus principles is endowed with a twisted structure in the one-variable situation, what will happen in the evolution process from the one-variable situation to the multivariable situation? Even though the multiple integral, the curvilinear integral and the surface integral are all integrals concerning multiple variables, they are not standard integrals of multiple variables but special integrals. Let's take function of three variables as an example. Set u equal u, x, y, z. We know its total differential is formula 1. Therefore, its indefinite integral of multiple variables is formula 2, which is the antiderivative of multiple variables. Strictly speaking, the curvilinear integrals are not indefinite integrals of multiple variables. But it is another matter when considering the situation where the curvilinear integral is independent of the path of integration. The integral of the high order is totally different from the multiple integral as this. The integral of the high order is the inverse process of the differential of the higher order, while the essence of the multiple integral is the combination of several integrals of one variable. Considering the division from the geometrical perspective, the multiple integral should be regarded as the body integral, which inherits with the curvilinear integral and the surface integral. Current principles of calculus fail to distinguish generality and particularity. Even for particularity, it only touches upon definite integrals, the exact equation being a special case. Scientific calculus requires functions of several variables, whereas the summation problem is no more than the specific application of the primitive function. In order to display the Stokes formula, current calculus incidentally touches upon finding the primitive function by means of the total differential, which is gratifying. However, the principal and subordinate relation is reversed in the meantime. For u equal ux y z, if the partial derivatives exist and are continuous, the mixed partial derivatives have nothing to do with the order of taking derivatives in terms of the different variables, and the total differential is integrable, which is formula 2. i.e. as this, the order of items in the accumulation doesn't matter. Therefore, the integral from x0 y0 z0 to xyz has nothing to do with the path of integration. For pxyz dx, plus qxyz dy, plus rxyz dz, if it is the total differential of uxyz, there exist formula 3, 4, 5. In addition, if the partial derivatives of p, q, r exist and are continuous, then these formulas can be deduced. Therefore, partial derivation of p for y equals to partial derivation of q for x, partial derivation of q for z equals to partial derivation of r for y, partial derivation of r for x equals to partial derivation of p for z. Formula 6 are tenable. Generally speaking, p dx plus q dy plus r dz, which is cobbled together, may not be a total differential of a certain function. If it isn't a total differential, there would not exist a primitive function of 3 variables. The so-called path of integration is no more than this, the essence of which is to transform the function of 3 variables into the function of 1 variable. Therefore, these formulas transform a non-integrable integral of 3 variables into an integrable definite integral of 1 variable. Obviously, different relations of x, y, z can result in different numbers. This is the inherent reason why the integral is related to the path of integration, which has nothing to do with the primitive function of several variables. How chaotic it is when people deal with the functions of several variables and high orders. It is more easier to see that the structure of current system of calculus principles is unreasonable. The current system of calculus principles, which involves mistakes listed above, has not provided the boost to the progress of calculus methods, and instead it has actually hindered the progress of calculus methods. In a word, such a system of principles of calculus has lost its proper meaning, so it should not be accepted by mathematics. Here, we have introduced the main points of Ding's, a brief discussion on the mistakes in current principles of calculus, published in Frontier Science. Newton and Leibniz vying for the right to invent calculus is a famous event in the history of science. The purpose that Newton published Philosophiae Naturalis Principium Mathematica in 1687 was to compete with Leibniz for the first discover of calculus. But why he postponed publishing his book until 1687 rather than 1665? If Newton himself had acknowledged that his calculus principle was complete and perfect, he would not do that. Quite on the contrary, the reason why Leibniz dared to publish his findings was that he was confident in his own work. On the other hand, in the development of calculus methods, the main contributors included the Bernoulli brothers, Euler, Lagrange, Laplace, Legendre, Fourier and Gauss. Among them, Euler made the most significant contribution. In terms of the teacher-student relationship, the Bernoulli brothers were friends and students of Leibniz, while Euler was a student of the Bernoulli brothers. On the contrary, after the establishment of the Taylor's formula by Taylor, British mathematics fell into stagnation. They could not get around the weakness of Newton's calculus theory. All these historical facts point to a conclusion that the rapid development of calculus methods was mainly due to thoughts of Leibniz but hardly had anything to do with the calculus theory, Cauchy established with the theory of limit, on the basis of Newton's thinking. After 1821, existing calculus methods were not optimized, nor were there any new calculus methods unveiled. On the other hand, calculus methods were far from exhaustive. For example, human beings cannot solve most differential equations until now. Speaking of which, friend, do you really understand the principle of calculus is wrong? All the information is listed here, and can be accessed by interested readers.